Success, money, the time, so as soon as I think that, get into that question, way it's really not nice. I feel like I mean, I figured it was very I hate to read it, but I'm not going to ignore it. There are things that don't understand. And
last semester. Yeah. Yeah. What did you take BioChem? Same thing. Yeah, the papers, we didn't have to do the whole thing last semester. We had to focus on one question. So I had to like review the whole paper yesterday to try and figure it out. They're tough.
still sad.
Welcome everyone. Can you hear me okay? It doesn't sound like the sound is up. Can you hear me in the back?
Your microphone's not on.
Actually, it is, but it's not. Something's not quite working as well. Let's go ahead and get started. I'd like to begin with prayer, and so is there a volunteer who would be willing to provide that for the class to get us going today? Please, thank you.
Our dear, kind, and gracious Heavenly Father, we are so grateful for this opportunity to be here on this Wednesday and to learn more of the fundamentals of biochemistry. We're so thankful for how far we've been able to get this semester amongst the pandemic, and we pray that we will be able to continue in safety and that we will be able to continue learning in a good manner. We're so thankful for Thy Spirit, and we ask Thy Spirit to be with us as we go throughout this class. And we love Thee, and we say these things humbly. In the name of Thy Son, Jesus Christ. Amen.
Amen. Thank you. So the long-awaited quiz is here. I have a hard copy to distribute that to the class. This same quiz is posted on Learning Suite under the Content tab. It will be due a week from today. It is a group quiz. It is a take-home quiz. It is sort of an open source quiz. You're welcome to look up things on the internet. You can refer to textbooks, papers, whatever that you wish. So, and you can have multiple people working on the quiz as part of a single group, up to 5 individuals. And participate as part of the single group. That means you can divide up the questions and reduce the workload in doing so. Are there questions about the quiz? No? Okay. will be due a week from today at 5 p.m. I will talk about ways to turn it in, but it is possible to submit either a hard copy or you can attach your quiz to an email. My preferred email is my departmental email. It's the one that's on the syllabus. If you send it to Learning Suite, eventually I'll probably see it, but I don't monitor messages on Learning Suite, and consequently, it may be a day or two before I see it. Okay. Also, I have another handout. We're going to be talking about mass spectrometry today. The book only gives a very cursory nod to mass spectrometry. We're going to talk about it in a little more detail. I feel that it is sufficiently important that we try to understand how mass spectrometry can be used in identifying proteins and other biological molecules that we're going to spend some time with it. Okay. All right. So that's sort of where we are headed. Are there questions? General questions about past material? I will mention that I am having office hours today. I probably won't get them started until about 3:10. I still have only the basic version of Zoom, and it requires that I compile an MP4 file, transfer it onto my thumb drive, and take it back to the department. So it takes a little while to get that done. But I will continue to post those recorded lectures to Learning Suite as well. All right. To begin with, so here are the things that we will be covering. We'll talk about methods to ionize biological molecules that are not destructive. We will talk about various mass detectors. These are the sort of the functional part of the mass spectrometers that you will talk about them in general ways. And then we're going to talk about applications, in particular how you go about doing protein identification. There are a couple alternative methods that we will consider. So that's sort of where we're headed. I'm going to go to, if I can, the last couple slides in the previous. Let's see, okay, how do I get that? Let's see the stop share. Slides. We have talked about electrophoretic techniques, and we've talked more about a particular method termed SDS-PAGE, or the SDS stands for sodium dodecyl sulfate, and the PAGE stands for polyacrylamide gel electrophoresis. I'm going to briefly mention another technique. This is called isoelectric focusing. This is usually done with a tube gel. So think of a small glass tube, maybe with an internal diameter of 5 millimeters. 5 millimeters. So fairly small, filled with a gel. And in that, you're going to have a series of proteins, and you're going to have a series of compounds that are called ampholytes. You don't need to know much about them except that these ampholytes will create pH zones. Okay? So as shown on this slide, there across this dimension, you can see that there are various zones. You can't really see the zones, but there are zones representing different pHs. These arise when you apply a voltage across this tube. So the tube is filled with gels, filled with liquid. You have something to allow for electrical conductivity, so a small amount of salt. You have these proteins, you have these amphiolites. Well, what's going to happen is that the proteins then will move toward, if they're negatively charged, they'll move towards the positive electrode. If they're positively charged, toward the negatively charged electrode, until they reach their isoelectric point. So as they move through these different pH zones, they will come to a zone where they will have no net charge. And as a consequence, then they're not attracted to the positive or negative electrode, and they become stationary. So this is termed isoelectric focusing. You're able then to separate proteins based on what? What is their isoelectric point? So they will move until they reach their isoelectric point, or the pH at which they achieve their electric neutrality. They'll have no net charge, and they become stationary. Okay. Very often, this is coupled with the SDS polyacrylamide gel electrophoresis. And this slide indicates, if you look at the top, you can see that there is a protein sample. This contains, let's say, the cytosol of a cell or a tissue homogenate, some collection of different proteins, and you want to separate them one from another. So we start off with this mixture up here, and the first thing that we do is we embed them in this tube with gel and carry out, and amphiolites, and carry out isoelectric focusing. So here we're going to separate them based on their isoelectric point, so their electrochemical properties, their charge as a function of pH. And this will do a moderately good job of separating proteins that have different or substantially different isoelectric points. What you then do is you're able to move the gel out of the tube, and you overlay that on the top of your polyacrylamide gel. So we actually literally lay this tube gel on this slab gel that's being held in this apparatus, and you apply some SDS, and this is going to now interact with the proteins present in this tube gel. You electrophoretically transfer the proteins in the tube gel to the slab gel. You have them treated with SDS, and now you apply a voltage and you cause them to move through the polyacrylamide gel based on their size. Okay, so smaller species are going to move through the polyacrylamide gel more rapidly. They have larger proteins, and you're going to then get separation based on size, whereas the isoelectric focusing separated things based on their isoelectric points. So you get two completely different properties being exploited for separation. So you move things across the top here based on their isoelectric point, then you transfer them to the slab gel, the polyacrylamide gel, and you separate them based on size. So that's described here in this slide, but in the end, you can end up with then a much more substantial separation of proteins using this two-dimensional gel electrophoretic approach as compared to either isoelectric focusing by itself or the SDS page by itself. And as shown here, this is, I think, a tissue homogenate. Each spot represents a protein. It's been stained with silver stain. And you can see hundreds, or dozens at least, of different proteins spread out one from another. This kind of approach can allow you to compare two different tissues. So you can look at, let's say, cancerous tissue versus normal tissue in an effort to try to understand what is different about the cancerous process. You could compare cells that were grown under one set of conditions to cells grown under a second set of conditions. And you can look at the content of those cells using this kind of approach and ask yourself, well, what are the differences in proteins? What are the protein responses to this kind of stimulus or this kind of treatment and so forth? So this has been used extensively in the past. It's still used to some degree currently, but it is not used as frequently as it once was. Okay, any questions about this? So this is two-dimensional, two representing isoelectric focusing followed by SDS page, gel electrophoresis. All right, we are now going to move on, if I can, to okay, I apologize to all for using slides. I will get away from these in a few minutes, but I think for right now, I will use these to introduce this topic. So mass spectrometry has been around for a long time. It's been around for over 100 years. Actually, it's been around since I think the 1890s. Okay, so a long time. However, up until a few decades ago, it could not be applied to biological molecules. Right? The reason being that there are two requirements to be able to carry out mass spectrometry, or to be able to measure a material in a mass spectrometer. The first of these is that it has to be ionized, has to have a charge on it. The second of these is the more problematic requirement, and that is it has to be in the vapor phase, in a gas phase. So as you think about biological molecules, the idea of trying to evaporate them is misguided. There is no way to evaporate biological molecules. If you think about your cookies left too long in the oven, as the smoke begins to pour out of the oven, you realize that you're not evaporating the sugars in the cookies. What you're doing is you are burning them, okay? And this happens with proteins, with lipids, sugars, nucleic acids. Whatever you do, when you try to heat them up to get them into the vapor phase, you simply pyrolyze them. You burn them up. So, until 1988, this was an insurmountable problem. But in 1988, two independent groups, found ways to bring about, or found ways to place biological molecules in the vapor phase without burning them, without destroying them. This led to these two groups both winning the Nobel Prize for their invention. Okay. That problem now has been, we will talk about those two methods, but that problem having been overcome, then mass spectrometry becomes a very powerful technique for the investigation of biological molecules. Mass spectrometers have become, have been developed into very, very accurate instruments, mass accurate instruments, and we'll talk about that as well. Okay. Okay, so if you look at the bottom of this slide, I'll introduce you to those two methods. Did you have a question? No. Okay. I'm going to introduce you to those two methods that are able to bring about ionization of biological molecules. The first of these is has a long name, so matrix-assisted laser desorption ionization. It's just referred to as MALDI, mass spec. MALDI represents the ionization technique. The mass spectrometer is next to the ionization source, so those molecules that are ionized and placed in the vapor phase are moved now into a mass detector. We'll talk about those in a minute. The second of these is electrospray ionization. It is a second independent method for bringing about both the ionization and the vaporization of biological molecules without heating them. Okay. So matrix desorption. You take your protein, and it turns out that for MALDI, you have to isolate the protein that you are investigating. This is a huge limitation. So it means that you have to perhaps do weeks or months worth of purification using all of those crazy methods that we talked about. So simple methods, chromatography, and in the end you end up with a small amount of this precious protein. And what you do is you take some of that and you mix it with a material that the method refers to as matrix. It turns out that you put it in a solution of a weak organic acid. The organic acid has to be able to absorb light at a wavelength that is remote from the absorbances of tryptophan and tyrosine. Okay, remember those two amino acid side groups absorb in the UV range. What you want to do is you want to have this matrix molecule, this organic acid, be something that is different. It's going to absorb at a different wavelength. These molecules, I don't know if I can draw it here, but they have generally aromatic benzene ring, okay, and they will have typically hydroxyl groups. Oops, it's a pretty bad hydroxyl group, and on two positions on the ring, and then the weak acid part is up here. Oops. Okay, so this is going to be a carboxylic acid group. Okay, pretty awful, but there it is. And so these molecules have a specific UV absorbance that is remote from the wavelength absorbed by proteins. These molecules are weakly acidic, but they are able to lose a proton and protonate the protein as part of this process. What you do is you take, you add your protein, you add the matrix molecule to a solution, you spot this on a plate, you allow that to dry. This plate then is a stainless steel plate, and then you shoot a beam of laser light on that spot. So, okay. What happens then is the following. The laser light is tuned to the wavelength of the absorption wavelength of the matrix molecule. That means all of that energy applied by the laser light is absorbed by the matrix molecule. It doesn't heat the protein, but it does heat the matrix molecule. And the consequence of that is that this matrix, this spot with matrix molecule will explode effectively. It will go immediately, dramatically into the vapor phase, and it will carry the protein with it. Any protein, the protein that you've purified and embedded in it will be carried with it. Okay. So you have an excess of the matrix molecule. That's simply because you have usually very little of your protein. Usually you have 100 or 1,000 or 10,000 times more of the matrix molecule than protein. But as the matrix molecule desorbs, okay, is lifted, vaporized off of the plate, it carries passively the protein molecules with it. So maybe as just an example, think of yourself being in Tokyo, rush hour, you're in the subway station, everybody's going home, and they're all exiting the subway train, and you're trying to get on. Okay, so the doors open, and 2,000, 3,000, 4,000 anxious commuters are going up the stairs, and you're trying to go down the stairs. What's going to happen to you? Well, they're going to carry you out of the train station, okay? Unless you can pin yourself on the wall and hope that they miss you. It's the same idea. The proteins are simply carried as this burst takes place with the laser light. It carries it away. It also confers a positive charge. Now, because this doesn't heat the protein is not fragmented, it is not broken, it is not destroyed. So here's a cartoon that shows this. Again, you mix your protein with the matrix molecule in a solvent. You spot this on a plate. This gives you the spot shown here. So this is the spot of the matrix dot. You then pulse it with laser light at a wavelength that is absorbed by the matrix molecule, and that leads to this sort of burst, explosive event where the matrix molecule is dramatically vaporized, instantaneously vaporized, and carries proteins with it into now your mass detector. The way that the mass detector manages this is that these molecules, in this case, are going to be positively charged, and there is an electrode at the back of the mass spectrometer that is negatively charged. These distances are not, I mean, this looks like there's a couple of feet between the matrix dot and the opening of the mass spectrometer, but that's not the case. These are very, very closely positioned one next to the other. Okay, yes?
So whenever you're setting this up, do you use a frequency of laser that will not be absorbed by the protein?
Yes.
That's how you get
Yes, you have to choose a matrix molecule whose absorption wavelength differs fairly dramatically from those of proteins, which are primarily due to tryptophan and tyrosine. They absorb at 280 nanometers of light. So you're going to choose something higher or lower so that when you pulse this with the laser light, all of the light energy is absorbed by the matrix molecule and not by the protein. Otherwise, you'd fry your protein. Yes?
So what is the protein like? What makes it positive again? Is that just
The weak acidic, the weak acid that represents the matrix molecule. So the matrix molecule is a weak acid, and it transfers a proton from a carboxyl group, forming carboxylate, but now positively charging the protein. Other questions? Questions from our online viewers? Okay, let's talk now about the second of these ionization methods. This is termed electrospray ionization, and it differs quite dramatically from MALDI. The sample is dissolved primarily in water. There usually is a small amount of a weak organic acid, usually a volatile organic acid, so we're not interested in forming a solid dot. What we would like to have is something that is easily removed by evaporation. So formic acid, trifluoroacetic acid are the two acids used to protonate proteins or other peptides present in this solution of water that you are forming. Okay, this is going to be pumped through a needle, a very fine, a very narrow diameter needle. And the needle is going to have a voltage applied to it. All right. So think of a very fine mist being produced by the needle. Very, very, very tiny droplets, and these will be suspended in air. Okay? They won't fall out, so they're not big enough to be rain droplets or dew, but they're more like fog in San Francisco, which just moves across off of the bay onto the streets of San Francisco. Those water droplets are very fine and will remain suspended in the atmosphere pretty much indefinitely. Okay. Now, as these droplets emerge from the needle, you will have moving across them in a perpendicular fashion a stream of warm nitrogen gas. And this tends to dry or cause evaporation to dry these droplets. And as a consequence of that, the droplets will become smaller. Okay? As you lose water through evaporation, the droplets quickly diminish in size, but the acidity, represented by the weak acid that's present, actually accumulates. Protons are not volatile, and consequently, the droplets will become progressively more acidic. You following me so far? So we have a weak acid present, formic acid, trifluoroacetic acid. Those protons they will come off of these acids and form hydronium ions, but as you shrink the droplets, you concentrate the acid. As the acidity becomes greater, virtually every group on the protein that can accept a positive charge will. So lysine side groups, the N-terminus amine, all of these histidines will now become positively charged because these droplets are becoming progressively more acidic. And ultimately, as you have all of these positively charged proteins and you have all of this accumulated acidity in the water, as it gets closer and closer together, at some point, you will have, again, an explosive event. You'll have a burst of the droplet because of electrostatic repulsion. Positively charged proteins will be too close and will push each other out into the atmosphere surrounding them. So this is what this looks like. Here is our electrospray needle, right over here. Now the beauty of electrospray ionization is that you can actually couple this needle to a separation column. Okay, remember with MALDI we had to purify our protein, and then we could spot it on the multiplane and irradiate it with laser light, and then we could examine what the protein was. But in this case, you can actually have you can separate proteins on a separation column and have them stream out the end of this electrospray needle and become charged. Now, if we look down in the corner here, notice that we start off with a larger, well, it's still a very small droplet. We start off with a droplet that has weak organic acid in that's going to confer protons to water and to proteins. We're going to have a stream of air going to move across this, so that so we have a stream of mist coming out of the needle. We're going to have a perpendicular stream of warm nitrogen gas move across this to dry these droplets. As they dry, they become smaller and smaller until ultimately the droplet can't hold together. The positively charged species in the droplet produce such strong repulsive forces, electrostatic repulsions, that it blows the droplet apart, and now our proteins are suspended in air. Okay? And they'll just hang there. I mean, if you can get fine particles from the fires in California suspended in the air that we breathe here, which we do, imagine that these are much, much smaller, and so these proteins will simply stay suspended in the air. They're positively charged, and they'll be attracted into our mass spectrometer. Again, you'll have a negatively charged electric plate back here somewhere, and it will attract these positively charged species into the mass spectrometer. Okay, yes?
There's a question. If the molecules are so small, how do they not just blow away from the air?
Some do, and so that's a good question. So you have the positive, the needle is positively charged, so as you protonate and cause your proteins to be positively charged, they'll be repelled away from the needle. The mass spectrometer, the opening of this, is going to have a negatively charged plate at the back. It will attract those, but the actual capture efficiency, do you want to guess what percentage of those protonated proteins that we capture with these methods? Any ideas? Yes? Yeah.
0.6%.
It's close. It's about 1%. Okay? So we actually are sacrificing 99% of the potential molecules, but we're getting a representation. We're getting a 1% sampling of the protein that's coming off at a given time, and it turns out that that's sufficient. These mass detectors are so sensitive that you can actually measure atomal, you'll have to look it up. It's got a lot of zeros before the number, okay? Atomal amounts of material. Yes?
So why is it that in this method we don't have to purify the protein again? Like, what's the stuff about the
Well,
protein?
the column is actually purifying the protein on the fly. Okay, but before you had to do all the column stuff. Now you're able to actually just run the chromatography material right onto the mass spectrometer. Okay, so literally if you take snapshots, that is, if you sample the stream of stuff coming off, you can measure literally hundreds of proteins as part of a single sample. So it has that particular advantage. Okay, other questions about these? These are complicated concepts. Yes?
Yeah, so what keeps the proteins from being obliterated in the explosion, or say, like whenever the
They're simply repelled. So think of two magnets pushing themselves apart. It doesn't blow up the magnets to simply have them repel. What it does do is it does cause them to escape from the droplet and be suspended in the air. Okay, so it's not as if you're, when I talk about explosion, there's no heat, there's no light. It's just simply the droplet is unable to remain as a droplet. You overcome the surface tension of the water molecules and you just splatter the material out into space. Yes?
Because the back wall of mass spectrometer is negatively charged, so it attracts.
Yes.
You have the proteins that stick to that surface.
They don't get that far, okay? Something else is going to happen to them, okay? But yes, in principle, they could go all the way to the back and crash into that. Yes?
When would you use multi over ESI?
Okay, we'll talk about that, but multi is, or historically has been used for a particular method called protein fingerprinting or peptide fingerprinting. And we'll talk about how that is accomplished probably next time. And that has been, historically has been used for that. It is used less and less. So for example, in the Benson building, we probably have somewhere between, we probably have close to a dozen mass spectrometers that can be used for protein identification. So these are biological mass spectrometers. We don't have any that have a multiplate. Okay, so the vast majority of mass spectrometers used commercially, used in research laboratories, pharmaceutical companies, you name it, typically don't have a multiplate. So it's becoming a little bit of an obsolete methodology. Other questions? These are good questions. Yes? Speak up so our...
Yeah, so the sample, is it a pure sample or are we just...
No, this doesn't have to be a pure sample. This is what is remarkable about electrospray ionization, is that you can actually purify the proteins one from another as you actually sample them and investigate them on the mass spectrometer. Okay? You have to have a good separation column in front of your electrospray needle, but that is not impossible to have. So. Okay. Okay, this will, I think, will be our last slide. I haven't actually come back to the board, have I? But we're going to talk about just sort of, there are three common commercial mass spectrometers available. And these are, and by mass, we use the term mass detector, mass analyzer, and mass spectrometer. They're all effectively synonymous. They all mean the same thing. This is the compartment in which you measure mass. How you measure mass is beyond what we'll be able to discuss here, but these instruments have the ability to measure differences in mass based on the behavior of these ions as they enter the mass detector, these tubes. Maybe the most common, or at least maybe the least expensive of these, and as a consequence the most common of these instruments, is called a quadrupole mass spectrometer. It actually has 4 rods that are electrically charged that guide ions, and depending on how you these rods have both a underlying direct current and an overlaid alternating current on them. And based on the frequency of the alternating current, only selected masses can go all the way through these 4 rods. The others are ejected, that is, they crash into the rods themselves. So that's one. Time of flight involves a flight tube. Usually it has an ion mirror at the back so that you extend the length of the tube, get better accuracy. But very simply put, the time it takes for an ion to move through the length of the tube is inversely proportional to its size. So small things arrive very quickly. Larger things take longer, and you have a detector that will time these, and so you're able to determine mass. There are trap instruments. The most sophisticated of these are Orbitrap instruments. We have 3 or 4 in the chemistry department. They cost about $1 million each, so they're not trivial. It's not pocket change for most of us. But they use a chamber, and they are able to capture an ion between a central electrode and sort of a spherical outer electrode. And based on how rapidly it orbits, the interior electrode is a reflection of its mass. And so the frequency of the orbit is going to be inversely proportional to the size. So smaller, goes around much more quickly, much shorter orbital times. Okay, I think we'll leave it here, and we'll talk about ways of identifying proteins or conducting another approach to identification called amino acid sequencing next time, and hopefully I can give you a sense of how this is accomplished. We're spending time on this because at this point in time, if you're talking about identifying a protein, you're talking about doing so with a mass spectrometer. It is almost the sole way in which you do protein identifications any longer. The mass spectrometry is also becoming very useful in studying other kinds of biological molecules, not nucleic acids. So, there's a whole different set of techniques and methods for doing peptide base sequencing and so forth. Those are very sophisticated, very robust. But for all the other kinds of molecules that we have in our body, when we talk about learning about studying these things and understanding what they are so that we can understand how they're made and regulated and so forth, this involves now mass spectrometry. So that's why we're spending all this extra time on it. Any questions? Yes, please.
So with these mass analyzer detector methods and especially the time of flight, can you come up with the actual mass, or is it all relative? Does that make sense? It's this one's bigger than this one's bigger than this one.
Yeah, that's an excellent question. So let me, if I can get rid of the screen here, let's stop sharing. Okay, so let me give you a sense of this. And so if I'm talking about quadrupole, its mass accuracy, okay, is approximately, a good one, is to a 1,000th of a mass unit. Okay, so you can distinguish between many, many different molecules because of the mass accuracy. Now, a time of flight instrument, if it's well tuned, to a 10,000th of a mass unit. And a Orbitrap, to 100 1,000th of a mass sheet. Consequently, these can literally keep track of tens of thousands of different molecules all coming off that separation column simultaneously because of the mass accuracy. Okay. All right, let me move this story forward about Rory. You haven't met Rory yet, but we went, this was many years ago, a group from our ward went up to Peterborough, New Hampshire, camped at the base of Mount Monadnock, a very popular climb, and this was over Thanksgiving weekend. We went up on a Friday, stayed the night, and then Saturday we were going to climb the mountain. Well, we got up Saturday morning. Well, before I do that, let me tell you about one of our campers. So there was a relatively new convert to the church, well, two converts, a woman and her son, who joined our ward, and the boy was sort of scout age, and he was invited and accepted the invitation to do this climb of Mount Monadnock. But he was sort of an inner city boy. He grew up and lived in a part of the Boston suburbs that was fairly economically depressed, and he had very little opportunity to get out and do things in the outdoors. And when he showed up, it was apparent that he was not well prepared for this hike. His shoes, his clothing, his sleeping bag, all of this indicated that this could be a challenging exercise for this young man. We got up Saturday morning, and the camp, it had snowed, and the camp was shrouded in fog. You could hardly see, you couldn't see from here to the back of the room. It was that densely foggy. And so this was a little bit intimidating, but the snow wasn't very deep and the trail looked safe. And so they decided they were going to climb Mount Monadnock anyway. So I'll have to tell you what happens next time. Anyway. Please join me if you have additional questions. I'll be back in my office in about 20 minutes. So please ask